Photography, the art of capturing a moment and keeping it that way forever. Behind every art, however, is a science, and in particular, chemistry. I am Dr. Ryan Westervolt, and today we will be talking about that art, that science, that beauty. Take a moment to set your expectations for this project. Done? Now take a moment to anticipate my shattering of them as you witness the sole greatest achievement of human creativity through a chemistry project the world has ever seen. We'll cover some basic topics like the history of photography, how cameras work and how they have worked, picture development, along with a scientific thesis through means of a simple lab. Then, as we go forward, witness pictures taken by yours truly and have their components dictated to your listening ears. Materials and buildings, clothes, the very essence of life. Stick around for the conclusion at the end with a glossary and bibliography for those daring enough to check them. Buckle your seatbelts, your pants, and your socks, because if you don't, they'll be knocked off by the end of this video. No. Short movie presentation. The first camera, named the Camera Obscura, was created near the year 1000 AD by the scientist now known as Alhazen. The funny thing, it wasn't even a real camera. Talk about an epic prank. No, it was just a pinhole in a wall able to project images comprised of varying shadow colors based on light blockage on whatever was outside the pinhole. In 1827, however, Joseph Nicephore, I wonder just how nice, took a photograph. However, it was more of a light-hardened image than one that utilized exposure. By placing a pewter plate with a special substance coated on, he was able to create a working camera that enabled him to capture an image through hardened plates, and this came after almost a decade of hard work. How he found out all those chemicals eludes me, because his patience must have been incredible. The picture, once ever so slightly more vivid than it is now, was always dingy, but eventually faded so that the image was hard to see. What a shame, considering it was only his life's work. The next great scientific breakthrough, how great was it considering I have to do this project because of these guys, was from Louis Daguerre. He worked at around the same time as Nicephore and ironically outdid him by both shortening exposure time and making pictures that didn't fade. Nicephore did do it first, however, securing his bragging rights. Despite this, Daguerre outlived dear old Joseph and created the daguerreotype, which has set the standard for all photography after it. This only added a few extra steps to cameras they had both made, and was made in collaboration with the late Nicephore and later, his son. Silver chloride was the secret ingredient to making the photos stay pristine enough where people could actually take a few guesses as to what they were of. Very shortly after, Daguerre and Nicephore II sold the rights of this wonderful machine to the government, progressing the science of photography. Following these achievements, with camera prototypes and additions now in place, the next new tech needed to be with the film and pictures. This led to Henry Talbot's development of negative in 1841. Paper with sensitive chemicals on it where light would burn an image into it based on short times of exposure. This led to the places on the photo with the most light to be the darkest on the paper, though when these negatives were developed, they were the opposite, or negative of that, and flipped the shading. Soon after, to one-up Talbot in 1851, Frederick Scoff Archer invented wet plate negatives that utilized wet plate development technology never seen before by the human eye, or again because we're not as primitive as he was. A simple invention in 1889 was the flexible film roll by George Eastman, allowing for film to be better utilized inside of cameras. As chemicals progressed and the lens worked better to capture light, Kodachrome, or color photography, for those who didn't know that, was invented in the 1930s by Eastman Kodak, which was utilized largely in the media for decades. Polaroid cameras were invented in the 60s, followed by the new digital age. I think that's supposed to say age. The new digital age, led by camera company Canon, who is still doing well today, thriving as the best company. Who would have thought, with their new cameras of electronics? These revolutionized picture quality and light quality. Lens developments also came, making photography widely used in the modern hip cool age. This takes us to now, where the last few decades have been slow but steady improvements to quality and lens. Mostly technological stuff, to be honest, no big breakthroughs. This concludes the epic chapter in this side of photography's history, but who knows what's to come? What's out in the dark? Old cameras. We love 'em, we hate 'em, we love to hate them, we hate to love them. They're tacky, slow, but somehow majestic. 35mm film, that's the one, the right one, that one that we used and we're focusing on. This camera type, like all others, has three main parts or sections. The optical section, housing the glass, viewer, mirrors, and lens that allow the light to form the picture. the mechanical section that includes all of the technology and is really just the camera's body, and the chemical section within this body housing the film and chemicals on it. The lens consists of the mirror, angled curved glass that make it up, and the shutter. The shutter is the thing that makes the clicky noise when your camera takes a picture, because it moves really fast open and closed to burn the picture in without ruining the film. The body and film work together to get the film into place and move the shutter in order for it to produce a picture successfully. All three components move in complete harmony, and if they did not, pictures would not work. They just would not. The main body of a camera contains a viewfinder for seeing through the camera, several tools to adjust the lens to let more or less light in, based on your surroundings, a battery to power the camera's flash and if it has electronic components, a film slot with film in it, the mirrors of the lens, and mainly just hold stuff. It's the part of the camera that you hold, and its job is just really to be there to contain stuff and make a shape that makes sense to take pictures and contain the components. Lenses work because light bounces off of other objects, and each object absorbs different colored light waves, so whatever is missing from the air in that direction is what the camera knows to fill in as the color of that object. The amount of light, or how badly the film is burned, is how shading in pictures come out realistically. This can also be affected by the aperture, or size of the hole that lets light through the lens. The chemicals inside the film go to work preserving this burned out image so that it may be developed later on. What are these chemicals? I don't hear you cry out because you taught us this in our chemistry teacher. I'll tell you anyways. The film is primarily made of emulsion, and the lens directs light into this to change the silver halides in the film. Based on how much light touches this silver, it changes to varying degrees, allowing for the picture to be painted. This about sums up how the camera itself works and gets film reader for development. Because that's the next section. Section 4. Development. Now on to Section 4, Development of the Film Purpose. What does each chemical do? Why do the steps in that order? How come it's so complicated? I don't know, but I'm going to find out. The first step is to have a darkroom, or a smaller void of light special container like the ones we use. Make sure the film has a spot with zero light, save red or green tones in a darkroom that won't affect the film. Any bright or white light would set off the silver halides I mentioned before, making the photographs useless. Next, you need to put the film to a series of chemicals to create negatives, or inversely colored versions of your pictures. In a darkroom, pictures are simply dipped in these chemicals, while in the small container we mentioned, you have to swish it around like a madman for a while. Now, before you dip the picture in any chemicals, you need to soak it in water of 21 degrees Celsius in order to have it be the right temperature for the developer. The first of these chemicals is called the developer, named for the process of, developing photographs. This allows for the partially formed silver halides to turn into a more permanent silver that maintains the picture, though too much developer can cause these crystals to form too large, ruining the picture and turning everything black. That's why to stop this process, you need to dip or shake the film with stop bath at 21 degrees Celsius next, which ends this enlarging silver process. It allows for the picture to come out just right in lighting when done correctly, so that nothing is too light or too dark. Because of it ending the process, this needs to be done immediately after. Don't use water after the developer, that's wrong. Don't take a break after or during the end of the developer, that's also wrong. Just add the stop bath for 2 minutes. Jeez. After the stop bath, quickly rinse out the container or picture twice with water for 15 seconds each time and move on to the next chemical, the fixer. Before you ask, yes, this also needs to be at 21 degrees Celsius. The fixer rids any of the silver halides that did not react with light enough, allowing for the dark parts of the picture to develop properly later on. Be careful with the disposal of this fluid, as it is extremely dangerous. I will refer to this multiple times because it is very important. Do not ingest this under any circumstance. If in the container, wash this out thoroughly with a fill and dump where you fill it, agitate it, and dump it 10 times. Next comes the PermaWash, a solution designed to help wash. PermaWash. You then wriggle your hands around like a prepubescent worm for 30 more 15-second rinse and dumps, or just put it in water in a darkroom. Seems easier in a darkroom. Finally, you gently swish your photo in PhotoFlow, copyrighted solution, which allows your picture to come out with no creases, smudges, or watermarks. By the end of the procedure, your pictures will be positives, and after drying for a day, they will look beautiful, so long as you follow the not at all complicated, super simple process listed above. Easiest thing ever. Can confirm that. Section 5. Return of the development process. This time, with science and big words. We all remember the heating part with water before the chemicals, yes? What if I told you the reason they all needed to be at 21 degrees Celsius? was so that the developer could undergo its chemical reaction properly. But, oh Ryan, my dear prince, knower of the great chemistry, what is this chemical reaction? Remember the silver halides mentioned before? These are most commonly in the form of silver iodide, silver bromide, and silver chloride. The significance of this is that these chemicals are easy to break apart in the reaction, kind of like speed dating, but not really, but maybe in a metaphorical sense. Anyways, the two AgBr Cl or IO molecules turn into a separate two molecules of silver, referred to sometimes as black silver, and a now invisible molecule of 2-bromine, iodine, or chlorine. Silver halides that have been broken down into pure silver by light from the other components are the only ones that can be affected by the developer, which contains metal, metol, phenidone, dimazone, and hydroquinone, all assisting in forming this blackened silver. After the developer has taken effect, making the film visible black and white, the stop bath is added. Where the developer was basic, the only point of the stop bath is to be acidic, neutralizing the developer and stopping its reaction, which can ruin the picture when it's gone too far. We know that the fixer makes the film permanent and allows for it not to be ruined when exposed to light. How does it do that? Magic? It feels that way sometimes. This project is pretty whack. This is because of two agents, sodium thiosulfate and ammonium thiosulfate. These two act as a protective barrier, protecting the once weak film with their strong chemical muscles. I'm not even going to try to say this equation out loud with the letters. Just know that the silver reacts with the thiosulfates and exchanges the extra bromine or iodine or chlorine. It goes from silver chloride and thiosulfate to sodium chloride and a silver thiosulfate compound, for example. None of the solutions or mixtures used in this lab are resistant to water. That means that against the ultimate unstoppable force that is water, they are nothing. This is the purpose of all the tedious, life-questioning wash and dumps. They clean out these powerful chemicals with nothing but tap water. Ha! The permawash is an ammonium sulfite and sodium sulfite mixture, two chemicals that assist in washing both the film and the container very effectively. These two chemicals are powerful cleaners because of their 100% distinctive properties. The photo flow used at the end is made of water, propylene glycol, water, and butyric octophenoxy. Because it is the last step, it does not merge with the other chemicals in a reaction. It simply fuses with the film partially, and whatever is left over gets eventually washed out. By the cleansing power of water. Water outlasts all. I will not fear. Fear is the mind killer, the death of all deaths. I shall let my fear wash over me, and when it is gone, only water will remain. It washed away the fear.